All right, today we are pulling back the curtain on one of the absolute workhorses of heavy fabrication, submerged arc welding. It's this kind of invisible force that literally builds the backbone of our modern world. So let's dive right in and see exactly how it works.
Now, this isn't some kind of riddle. This is the entire idea behind submerged arc welding, or SAW as you'll hear it called. You see, unlike most welding where you've got this brilliant, blinding arc, the real magic of SAW happens completely hidden from sight. And that one unique feature, well, that's the key to its incredible power and efficiency. So what exactly is it? Well, at its core, SAW uses an electric arc to melt a wire electrode that's fed continuously, and it fuses that wire with the base metal, the workpiece. But the crucial part, the real secret ingredient, is this blanket of granular, kind of sand-like material called flux. This flux totally submerges the arc, which, you guessed it, is exactly where the process gets its name.
And believe me, this isn't some niche process for small jobs. No way. SAW is the absolute go-to for massive scale projects. We're talking about building the colossal hulls of ships, fabricating the high-pressure vessels you see in power plants and refineries, and creating miles and miles of large diameter pipes. Seriously, when you need to lay down a lot of high-quality metal and you need to do it fast, SAW is pretty much the undisputed champion.
Okay, so now let's get right to the heart of it. How in the world does a weld actually happen if you can't even see the arc? It's time to take a look under that protective flux blanket and see what's really going on. This image right here, it perfectly visualizes that whole hidden process. You've got a continuous wire electrode feeding down towards the workpiece. As it gets close, bam, an arc ignites, but it's completely buried inside that pile of granular flux. The intense heat melts everything, the electrode, the base metal, and the flux right around it. This melted flux forms a liquid shield called molten slag, and this stuff is critical. It protects that molten weld pole from the air, preventing impurities and ensuring you get a perfectly clean, super strong weld.
So let's just break it down into 5 simple steps. First, you cover the joint with that granular flux. Then the arc strikes, totally hidden underneath it. The electrode wire feeds in, nice and continuous, and melts. That molten flux turns into a liquid slag, which shields the whole weld. And then finally, once everything cools down, you just chip away that hardened slag, and what's underneath? A flawless weld.
A great weld isn't just about the process. It's about the materials you use. In SAW, the electrode wire and the flux, they're a team. They have to work together. Choosing the right combination is a lot like a chef picking the perfect ingredients. It determines everything about the final outcome, from the weld strength all the way down to its chemical properties.
Now, flux isn't just flux. It comes in 2 main flavors. You can think of neutral flux as kind of a bodyguard. Its main job is just to shield the weld without really changing its chemistry. This makes it perfect for building up really thick materials with lots of passes, like on a nuclear pressure vessel. On the other hand, active and alloy fluxes, they're more like chemists. They don't just shield the weld, they actually add specific elements to it, like deoxidizers to handle rust or mill scale, or alloys to improve toughness. And they often get the job done in a single high-speed pass. So the really crucial thing to get is that flux is a multi-talented superstar. It shields, it helps stabilize the electric arc, it can fine-tune the weld's chemical makeup, it cleans the molten pool by pulling out impurities, it helps shape the final weld bead, and it even controls how quickly the whole thing cools down. It is a highly engineered material that does so much more than just cover the arc.
Okay, so if you've ever looked at welding consumables, you've probably seen this string of letters and numbers that looks like some kind of secret code. Well, it's not. It's the AWS classification, and it tells you absolutely everything you need to know about what that wire and flux combo can do. So let's learn how to read it.
Here's a perfect example of what you might see on a package. F7A 2-EM12K. I know, it looks a little intimidating, but every single part of this code has a specific and really important meaning. We're going to break it down piece by piece.
At this table right here, this is our key. Let's walk through it. The first half, F7A2, is all about the flux and the final properties of the weld. F, that's easy, it's for flux. The 7 means a minimum tensile strength of 70,000 psi. A tells you it's for an as-welded condition, so no extra heat treating needed. And that 2, that tells you its toughness, specifically that it can handle impacts at cold temperatures. Now, the second half, EM12K, describes the electrode wire itself. E stands for electrode. M means it has medium manganese content. 12 tells us the carbon content, which is about 0.12%. and K indicates it designed for silicon-killed steel, a super common type of steel. See, it's not a secret code at all. It's a complete data sheet.
Now, knowing your ingredients is only half the battle. The true craft of submerged arc welding comes from mastering the process variables. A skilled operator knows exactly how to balance all these different settings to get a flawless weld, every single time. Let's take a look at what those key variables are.
So these are the main dials the operator has to turn, so to speak. You've got welding current, or amperage, which is all about the heat and penetration. There's arc voltage, which affects the width and shape of the weld. Travel speed, pretty self-explanatory, how fast you're moving. Then you've got the electrode's diameter and extension, how much wire sticks out. And of course, the type of flux we just talked about.
Okay, let's just take one of those variables to see how this all works. What do you think happens when you crank up the amperage, the welding current?
This slide shows it perfectly. As you increase the current, moving from left to right, you can see the weld is penetrating deeper and deeper into the base metal. You're also depositing metal faster, which is fantastic for productivity. But it's a balancing act. If you push that current too high for the thickness of the material, you risk just melting straight through it. That's called burn through. And this cause and effect relationship, it's true for every single variable on that list.
And this right here is probably the most critical takeaway about the craft of welding. None of these variables exist in a vacuum. You can think of it like driving a car, right? Hitting the gas, that's your current, without adjusting your steering, that's your travel speed, is probably going to end badly. If you speed up, you might need more current to get the same penetration. If you change your voltage, it could affect the bead shape. It's a complex dance, and a skilled welder or a well-programmed automated system has to manage these relationships perfectly.
So, after looking under the hood of this really powerful process, what's the final verdict? Well, like any technology, submerged arc welding has areas where it absolutely shines and other areas where, a different process might be a better choice.
So let's look at the scorecard. On the advantages side, the list is seriously impressive. You get incredibly high deposition rates, which means you could finish huge jobs fast. The weld quality is excellent, with deep, consistent penetration. And because that arc is submerged, there's no arc flash and very little smoke, which makes for a much better working environment. Plus, it's perfect for automation. Now, the limitations? Well, you're pretty much stuck welding in the flat or horizontal position. Gravity is your friend here. You do have to clean off the slag after every pass. And the flux has to be kept dry, because if it absorbs moisture, you can get defects in the weld. And finally, it's just too powerful for really thin materials.
Submerged arc welding has been a cornerstone of heavy industry for decades. But as our ability to automate and precisely control all these complex variables gets better and better, its potential just keeps growing. So the question isn't if this invisible force will continue to build our world, but what incredible new structures it's going to create next.